Good day. I am Charlotte Atakima from the Kwame Nkrumah University of Science and Technology, Kumasi, Ghana, and I am excited to present my work to you. Conversion of waste plastics to fuel using ZSM5 catalyst synthesized from kaolin clay and rice husk. This research was conducted for my MPhil thesis and was supervised by Professor Johannes Awoja. The United Nations Environment Assembly has listed plastic pollution as a serious global environmental problem in the UNEP Resolution 5 for 14 resolutions to address global environmental concerns. But why are waste plastics such a concern? It is because they are made up of hydrocarbons and are not easily degraded in the natural environment. How do we address plastic pollution? Do we landfill? The high volume to weight ratio of waste plastics makes this not suitable. Do we incinerate? This does not allow us to maximize the potential of waste plastics. However, we can convert waste plastics to fuel. This will generate an alternative fuel source and ensure a circular economy, aligning with SDG 12, responsible consumption and production. Pyrolysis is a technology which enables the conversion of waste plastics to fuel, but a catalyst is often required in order to reduce the process requirements and to increase the yield of desired products. ZSM5 is a notable catalyst which is used for pyrolysis of waste plastics to fuel, but it is expensive. ZSM5 has 10 membered rings on sinusoidal rings. It has Lewis acid sides and Bronsted acid sides, and these enable the catalytic conversion of waste plastics to fuel. This is the molecular structure of ZSM5. ZSM5 can be synthesized from clay, and this will reduce the cost involved in converting waste plastics to fuel when ZSM5 is employed. Clay contains silica and alumina, and these are the basic building blocks in the ZSM5 framework. The silicon to aluminum ratio in clay is lower than the silicon to aluminum ratio that is needed for the ZSM5 framework. So the clay usually will have to be pre-treated in order to increase the silicon to aluminum ratio. Extra silica can also be added to the clay to increase the silicon to aluminum ratio. The main objective of this research was to convert waste high-density polyethylene into liquid gasoline-range fuel using ZSM5 derived from kaolin clay and rice husk. Specifically, this research sought to purify and characterize kaolin clay samples, extract silica from rice husk and characterize the extracted silica, synthesize ZSM5 using different proportions of purified kaolin clay and silica from rice husk, and convert waste HDPE to fuel using the asynthesized ZSM5 catalyst and characterize the fuel produced. Research methodology. Rice husk was obtained from a farm. It was purified by acid leaching to remove metallic impurities and calcination to remove organic impurities. The The silica in the rice husk was extracted using sodium hydroxide solution and precipitated using hydrochloric acid. The white silica precipitate was washed and dried and pulverized. The kaolin clay was purified by calcination to convert the kaolin to metakaolin and acid leaching to remove metallic impurities. Sodium hydroxide was used as a mineralizing agent for the synthesis process. Tetrapropyl ammonium bromide was used as a structure directing agent, and water was used as a solvent. 3 samples were used for the ZSM5 synthesis. The first sample, named ZCS1, contained only the clay sample. ZCS2 contained the clay sample and silica from rice husk to give a silicon to aluminum mass ratio of 30. ZCS3 contained the clay sample with additional silica to give a silicon to aluminum mass ratio of 40. The samples were aged. All key parameters for the synthesis process, like aging conditions, amount of structure directing agent, amount of mineralizing agent, amount of solvent, crystallization time and temperature, were kept constant. The ZSM5 samples were aged in a hydrothermal autoclave reactor for 48 hours. They were crystallized in a Mehmet oven for 24 hours, and the resultant ZSM5 was filtered, washed, and dried. They were then subjected to characterization techniques to determine whether ZSM5 had actually been produced. The successful ZSM5 that was produced was in the ZCS2 sample, and this was divided into 2 variants, sodium ZSM5 and hydrogen ZSM5, and they were combined with high-density polyethylene pellets and used for pyrolysis to obtain the pyrolysis fuel. Results and discussions. The kaolin clay was subjected to thermogravimetric analysis to determine its decomposition pattern. The decomposition began with the removal of water from 60 degrees Celsius to 106 degrees Celsius, and organic impurities and carbonates were removed at 428 degrees Celsius, followed by the reorganization of kaolin into metakaolin at 611 degrees Celsius, and the metakaolin was maintained up until 900 degrees Celsius. FTIR spectra of raw kaolin clay, calcined, and acid-leached kaolin clay. Hydroxyl bond vibrations were observed at 369 per centimeters, 3,692 per centimeters, and 1,639 per centimeters in the raw kaolin clay, but these were absent in the calcined clay and the acid-leached clay, indicating that there was removal of water during calcination. The kaolinite groups, represented by the silicon-oxygen aluminium bond vibrations and the aluminium hydroxyl group bond vibrations, were also present in the raw kaolin clay at 1,005 centimeters and 913 per centimeters for the silicon oxygen aluminium bond vibration and the aluminium hydroxyl bond vibrations respectively. But these were fused in the metakaolinites into metakaolinite in the calcined sample and the acid-leach sample. Silicon oxygen bond vibrations were also observed in the raw kaolin clay as well as the calcined and acid-leached samples. XRD spectra of raw and calcined kaolin clay. The XRD spectra reveal the presence of quartz as well as kaolinite in the clay samples. These were the main minerals in the sample. Elemental analysis of the kaolin clay was conducted using X-ray fluorescence spectroscopy. The main elements which were observed were silicon, aluminium, iron, magnesium, and calcium. The silicon to aluminum ratio of the calcined clay was 2.54. After acid leaching in 6 molar HCl in a ratio of 1:5 for 12 hours, the silicon to aluminum ratio increased to 12.77. When the acid leaching was continued for about 37 hours in 6 molar HCl in a ratio of 1:10, the silicon to aluminum ratio increased to 19.76, and this was used for the synthesis. FTIR spectrum of rice husk silica. The FTIR spectrum reveals silicon-oxygen bond vibrations at 1,648 per centimeters, 1,070.9 per centimeters, and 803.7 per centimeters. It also reveals the silicon-oxygen-silicon bond bending vibrations as 798.37 per centimeters, confirming the presence of silica in the extracted sample. XRD spectrum of rice husk silica. The XRD spectrum revealed that the silica obtained was amorphous, and when it was analyzed using expert high score, it matched with the silicon oxide pattern in ICSD. FTIR analysis were done on the different zeolite samples, and their spectra were compared to the commercial ZSM5. The aluminosilicate framework vibration, which is present in the commercial ZSM5, is also present in ZCS1, but the peak is sharper in the commercial ZSM5 but broader in ZCS1. The silicon-oxygen bond vibrations are also present in ZCS1 as are observed in the commercial ZSM5. However, the pentosyl unit vibration, which is very significant in identifying the ZSM5 framework in a sample, is present in the commercial ZSM5 but absent in ZCS1, indicating that the zeolite phase did not form in ZCS1. XRD analysis was done to confirm the presence of ZSM5 in the ZCS1 sample. The the ZSM5 characteristic peaks at 8 to 9 and 22 to 25, which are present in the commercial ZSM5, are absent in ZCS1, indicating that ZSM5 did not form in the ZCS1 sample. The second sample, ZCS2, was also taken through FTIR analysis, and its spectrum was compared to the commercial ZSM5. The aluminosilicate framework vibration, which is present in the commercial ZSM5, was also observed in ZCS2. The silicon oxygen bond vibrations are present in ZCS2 as are observed in the commercial sample. More significantly, the pentasyl unit vibration is present in the ZCS2 as it is observed in the commercial ZSM5 sample, indicating that there was formation of ZSM5 in the ZCS2 sample. XRD analysis was also done to confirm the presence of ZSM5 in the ZCS2 sample, and this spectrum was compared to that of the commercial ZSM5. The characteristic diffraction pattern at 8 to 9 degrees is present in ZCS2 as it is observed in the commercial zeolite. The prominent one at 22 to 25 is also present in ZCS2 as it is observed in the commercial ZSM5, indicating that there was indeed the formation of ZSM5 in the ZCS2 sample. FTIR spectra of the commercial ZSM5 and ZCS3. The aluminosilicate framework vibration, which is present in the commercial ZSM5 spectrum, was present in ZCS3 but broader in ZCS3 than it is in the commercial ZSM5 and with a lesser intensity. The silicon-oxygen bond vibrations were present in ZCS3 as are observed in the commercial ZSM5. The pentasol unit vibration in the commercial ZSM5 is also observed in ZCS3, but its intensity in ZCS3 is low, indicating that there is some formation of ZSM5 in the ZCS3 sample. XRD analysis was also done to confirm the presence of ZSM5 in the ZCS3 sample. The characteristic diffraction pattern at 8 to 9 degrees was observed in ZCS3 but at very low intensities. The characteristic diffraction pattern at 22 to 23 was also present in ZCS3 but at a very low intensity. This indicated that there was some formation, very little formation of ZSM5 in the ZCS3 sample. The prominent peak, which was observed in the ZCS3 spectrum but not present in the commercial sample, was analyzed with expert high score and it corresponded to sodium aluminium silicate in the ICSD database. ZCS2, which was significantly similar to the commercial ZSM5, was then used for further characterization and application. Thermogravimetric analysis was done on ZCS2, and the decomposition pattern reveals the removal of water, followed by the removal of the bromide ion, followed by the removal of the tetrapropyl group, followed by the removal of the ammonium ion, leaving behind the stable ZSM5 catalyst. Scanning electron micrographs of ZCS2 was also taken to determine its surface morphology. At 20 microns, it was observed that the synthesized ZSM5 in the ZCS2 sample had a spherical morphology, and at 2 microns, it was observed that it had a porous surface as it is expected of ZSM5. ZCS2 was divided into two variants and used for the pyrolysis experiment. PF001 was the liquid fuel obtained when the sodium form of the ZCS2 was used. PF002 was the proton form of the ZCS2. PF003 was the liquid fuel obtained when no catalyst was used. The physicochemical properties, density, viscosity, refractive index, and flash point were taken and compared to that of petrol and diesel The densities, viscosities, and refractive index of the three fuel samples corresponded to petrol. However, the flash points of the three samples were higher than petrol but lower than diesel, and this could be attributed to moisture and impurities. The hydrogen form of the catalyst exhibited the highest activity, giving a yield of 65% at a process duration of 1 hour, whilst the sodium form gave a yield of 54.43% at a slightly longer retention time of 1 hour 15 minutes. The pyrolysis process without a catalyst gave a liquid fuel yield of 51.79% at a longer retention time of 2 hours. And this indicates that the synthesized catalyst indeed improved the desired liquid fuel yield at lower retention times. FTIR analysis was done on the pyrolysis fuel to determine the functional groups that were present. Alkyl CH stretching vibrations were observed in all three samples. Secondary carbon-hydrogen bending vibrations were also observed in all three samples. Carbon-carbon double bond stretching vibrations were observed in all three samples, as well as out of the plane CH vibrations of aromatic groups. This indicates that alkenes and aromatic groups are present in the fuel as it is expected of petrol. In conclusion, ZSM5 catalyst was successfully synthesized in the ZCS2 sample, and its XRD and FTIR spectra are similar to the commercial zeolite. Waste high-density polyethylene was successfully converted to fuel using the asynthesized ZSM5 catalyst derived from clay and rice husk. Conversion of waste plastics to fuel promotes clean water and sanitation, protects life below water, and protects life on land, helping us to achieve SDG 6, SDG 14, and SDG 15. I recommend that further study be conducted on the upscaling of the production of ZSM5 from kaolin clay and rice husk for process commercialization. These are some references from my work. Thank you.